Oh, hey there. You caught me reading my bedtime story from my classical mechanics textbook. Tonight, I was just reading the chapter about the rotational motion of rigid bodies. There's some fascinating stuff in this world.
Well, that was pretty interesting. What happened there?
I'm glad you asked. So depending on what axis you flip the object in, you will get different rotations. If I flip the deck of cards around an axis, sticking straight through the face of the deck, the same thing happens when I flip the deck around an axis pointing through the top of the deck. It rotates cleanly around that axis and around no other axes. But something different happens when I flip this deck of cards around the axis that points straight through the side of the deck. As you see, the deck starts to rotate on this axis, but soon tumbles and turns around the other axes too. To really see what is happening here, we must first understand a little bit about the motion of rotating objects. We call this deck of cards a rigid body. A rigid body is an object made up of n number of particles that are fixed in place relative to each other. This is basically saying that it is a solid object. It turns out that every rigid body has three axes called the principal axes. These are the axes that when the object rotates about this axis, it only spins around this axis and not in any other direction. We will label these axis 1, axis 2, and axis 3. So we see that our deck of cards can rotate around each principal axis. Of course, the deck of cards can rotate in any direction, but this is just a combination of rotation around the three principal axes. Let us now introduce three properties of this rotational motion: angular momentum, written as L, moment of inertia, written as lambda, and angular velocity, written as omega. Each principal axis has a different angular momentum, moment of inertia, and angular velocity that are specific to that axis. For each axis, these properties are related by this equation. The angular momentum about that axis equals the moment of inertia times the angular velocity, or L equals lambda omega. The angular momentum of a spinning object is just like the momentum of an object moving in a straight line. Just as the momentum of a moving object makes it harder to stop, the angular momentum of a rotating object makes it harder to stop spinning. The angular momentum around an axis of a rotating object depends on the moment of inertia and the angular velocity. The moment of inertia is comparable to the mass of our straight line motion object. Its equation shows that the more mass there is away from the axis of rotation, the larger the moment of inertia will be. So for our cards, we have a large moment of inertia, a medium moment of inertia, and a small moment of inertia. Last but not least, the angular velocity of our rotating object is just how fast it is spinning. Now you know how to quantify the rotation of an object, namely through its angular momentum, moment of inertia, and angular velocity, around one of the three principal axes. But we still need some equations of motion that will help us analyze this deck of cards. Let's go to our physicist in the lab, who can explain this rotational motion mathematically. Thanks, David. So for any free rotation of an object around its center of mass, we can use a special form of Euler's equations. The equation is the first moment of inertia times the change in the first angular velocity equals the second moment of inertia minus the third moment of inertia, all times the second angular velocity and third angular velocity. One interesting quantity here is the time derivative of angular velocity. This is just the acceleration of the rotation of the object. So if our acceleration equals 0, then our object rotates at a constant angular velocity, without speeding up or slowing down. There are two other equations with the same form for the two other principal axes. So based on the angular velocities and moments of inertia around each principal axis, we can see how the angular velocity around each axis changes. For example, say our deck of cards was only rotating around axis number 2. This means that the angular velocity around the other axes, number 1 and 3, are 0. Since all of our equations include either the angular velocity for 1 or 2 on the right side, all of the acceleration of rotation go to 0. This is exactly what we see. The rotation is constant around axis 2 and doesn't rotate around axis 1 or axis 3. Then why does this deck of cards tumble and spin around all its axes when I spin it around its second axis? In real life, you cannot spin an object perfectly on its axis. By the nature of our experiment, the other axes will have some rotation as well. At the moment we throw the deck on its second axis, the other two axes have very, very small but still non-zero angular velocities. To see how these small rotations play out, let's look at our equations one more time. We have some angular velocity, omega 2, since our object starts spinning on its second axis. We also see that even though omega 1 and omega 3 are very small, they do not equal 0. We can assume, for at least the short future, that omega 2 is constant, because omega 2 dot consists of omega 1 and omega 3, which are very small. The two equations for omega 1 dot and omega 3 dot can now be solved to find omega 1. Since omega 2 is approximated as a constant, our right sides become a constant times an angular velocity. We start by taking the derivative of omega 1 dot. Omega 3 dot can now be substituted in to get this equation. This is just a second-order differential equation that can be solved using differential calculus. There are two different solutions based on whether the constant in the bracket is positive or negative. It is positive whenever lambda 2 is greater than both lambda 1 and lambda 3, or when is less than both lambda 1 and lambda 3. Our solution for omega 1 then becomes a sine or cosine function that oscillates back and forth with time. Since omega 3 is proportional to omega 1 dot, it also oscillates in the same manner as omega 1. Thus, the rotation on the other axes stay very small and just oscillate back and forth. This is what we saw when we flipped the cards on axis 1 or 3. But our solution for when the constant is negative shows the real magic. This happens when lambda 2 is between lambda 1 and lambda 3. The solution for omega 1 is now exponential and increases dramatically with time. As time increases, the angular velocity on axis 1 grows and grows until the object is tumbling out of alignment. This is why our deck of cards tumbles and spins in all directions. We spun it around the unstable axis that has the middle moment of inertia, leading to exponential change in the rotation around the other axes. So we have seen that there is stable rotation around the maximal and minimal axes. But when rotating around the middle axis, there is tumbling and spinning in all directions.